Hi everyone, welcome back to Data Cadence. My name is Rahul and I work as a senior applied research scientist. And in this particular video, we are going to talk about one of the most important and one of the most famous parameter efficient fine tuning techniques that exist, that is known as LoRA or low rank adaptation. Now, in one of the previous videos, we had talked about RAG versus prompt engineering versus fine tuning. And in that, I had briefly touched up upon two types of fine tuning of large language models. First one is the complete or the full parameter based fine tuning, and second one is the parameter efficient based fine tuning. So in this particular video, we will talk about LoRA, one of the most famous methods under the parameter efficient fine tuning techniques that exist out there. So let's begin. So LoRA stands for low rank adaptation, and like I mentioned, it's one of the parameter efficient fine tuning techniques. There are many more, but LoRA and QLoRA, which is a variant of LoRA, is widely used in the industry for fine tuning of large language models. And the core idea behind LoRA or PEFT for that matter is to basically try to fine tune these large language models which have billions of parameters on a consumer grade GPU. So say for example, you have a very large model, say 80 gigabytes. So think of it something like Llama 370 billion or maybe even Llama 3.1405 billion, which is the latest release from Meta AI. And you want to do some sort of fine tuning on a consumer grade GPU instead of a very large GPU. So you have basically two types of GPUs. First one is a very specialized and a heavy GPU. So an example could be NVIDIA A100 that has VRAM up to 80 GBs or even up to 100 GBs if you stack multiple of them. And on the other hand, you have consumer grade GPUs like NVIDIA A10G, which is a Tensor Core GPU, or maybe Tesla T4, that is another of the NVIDIA's consumer grade GPUs, which typically have VRAMs like 16 GB or say 24 GB in case of NVIDIA A10G. And the idea is, can I somehow load this particular larger model onto one of these consumer grade GPUs that is converted to a smaller model and fit this on a smaller GPU and then perform tasks like fine tuning or say running a stable diffusion job and so on. Now LoRa modifies the architecture of the transformers by injecting trainable rank decomposition matrices into each layer of the frozen pre-trained model weights of the transformer. If you don't really understand this, don't worry, you will understand it by the end of this particular video. Just stick till the end. And then fine tuning involves copying the weights from a pre-trained network and tuning them on the downstream task. And that's what we discussed is fine tuning, right? Because you have a particular downstream task at hand. Now it could be say translation or summarization or some particular understanding of a highly specialized context or domain. And you essentially want to learn a new set of weights for each of these downstream tasks that you have, and that's what is fine tuning. Now, like we mentioned, fine tuning could be done in multiple ways. The first one is a full parameter fine tuning, in which essentially you update all the model weights. And the drawback is that the weight matrices can be very large. So if you consider a Llama 7 billion or a Llama 213 billion, so you do have 7 billion and 13 billion weights respectively, and that could be a lot to load on a consumer grade GPU. Now all the weights get updated repeatedly for multiple epochs, and that is where the problem is, because if you are having so many parameters or weights in your particular model, updating each and every layer and doing a complete parameter fine tuning across all the layers can be very much computationally expensive, and it can also be expensive in terms of a dollar value, because you would have to have a higher GPU RAM instances and you would have to run them for multiple hours, and that would just rack up your infra costs, right? So storing and updating these weights require a lot of memory, which limits fine tuning to large GPUs or even GPU clusters if your model is really large. And how is LoRa different? So instead of updating the weights directly, the idea is that can we somehow track the weight changes instead of updating the original weights directly? And these weight changes are tracked in two separate smaller matrices that get multiplied together to form the matrix of the same size as the model's original weight matrix. So what I mean by that is, consider a particular layer in any given model. Say you have the original model weights here. And now instead of updating these original model weights, can you somehow have a weight changes matrix which comes out from LoRa? And how does it come out? We'll just talk about that. But instead of updating the original weights, can you somehow track the weight changes using low rank adaptation to end up with a fine-tuned model weights? So instead of updating the numbers in this particular matrix, I add another matrix to this original model weights and try to end up with a fine-tuned model weights. Now the question is, how do you obtain this LoRa weight change matrix, or how do you basically track your changes and add it to the original model weights? So that's where the low rank part comes in. So you multiply two low rank decomposable matrices. So say for example, you have a 5 cross 1 matrix and you have a 1 cross 5 matrix, And a rank of a matrix is basically the number of linearly independent columns or rows for that matter in a given matrix. So that's what you call as the rank of a matrix. And here you have a rank 1 matrix in both the cases. And that's why it's termed as a low rank matrices. And here you see if you multiply a 5 cross 1 matrix with a 1 cross 5 matrix, you would end up with a 5 cross 5 matrix. And that's how this LoRa weight changes matrix is being computed. And the advantage is that for the above example, as you saw, you only have to deal with 10 trainable parameters instead of 25. So 5 for this first matrix and 5 for this second matrix, and you would still end up with 25 parameters, but you would only have 10 learnable or 10 trainable parameters in terms of the number of parameters that you would want to update. And now this will lead to a lower precision, of course, but increasing the rank of the LoRa matrices will increase the precision. That's pretty intuitive, because if you keep on increasing the rank, you would go towards the complete or the full parameter fine tuning route, and therefore it will lead to higher precision weight changes, and that's pretty intuitive, right? Now the question that you might ask is, does rank really matter? So yes, rank matters. The theory is that the downstream tasks on which you are trying to do some sort of fine tuning are intrinsically low rank. That's what they found out in the paper, because the specific task in most cases is a small subset of what the model has already learned during the pre-training or the instruction tuning phase, right? And this hypothesis was tested in the original paper and they get really good results. So long story short, the low rank tasks, the downstream tasks that you are trying to fine tune on are intrinsically low rank, and therefore this particular hypothesis of injecting the product of two low rank decomposable matrices works very well in practice. So areas where higher rank might be helpful, that could be another question. So when you want to teach the model some sort of complex behavior, or you want to teach the behavior that contradicts or fail, or it falls outside the scope of previous pre-training or training of the model, in such a scenario, you might want to go for a higher value of the rank that you select, right? Now follow up to LoRa, there was another paper called QLoRA or quantized LoRa, which was a natural extension of the LoRa paper via quantization. Now you can learn more about quantization. That is again an in-depth or a detailed topic for another video. But the idea is that typically when you have all of these weights stored in your models and multiple layers, you would have the weight stored as a 16-bit or 32-bit floating point number. And the idea is to reduce that to a 4-bit number. And the way they implemented that, they managed to recover the original precision of the model. This might sound impossible, but they did it in a very clever way. So the core idea is that they exploited the fact that all these parameters fall essentially onto a normal distribution, and these 4-bit numbers where they fall in the normal distribution, using that you can recover the original precision. So think of QLoRA as LoRa 2.0 or the upgraded version of LoRa, and it uses even less memory, even lesser memory with recoverable quantization. So it's a further optimized version of LoRa, and QLoRA is one of the most recent techniques that have been out there, and yes, definitely it's one of those techniques that you will see across a lot of these models. So the paper also had two other critical findings. The first one was that training all layers of the network is indeed necessary to match the performance of the full parameter fine tuning. So of course there is no magic pill, that there is always a trade-off, right? If you want to have a larger model fit on a smaller GPU, or if you just want to, instead of updating the original weights, only update the weight changes or track the changes, that will not give you the performance that you will get when you are doing a full parameter fine tuning. So yes, the trade-off is always there. You need to train all the layers of the network if you want to match the performance of a full parameter fine tuning. You can probably get close, but you can't really match the performance, right? And then the another conclusion or another finding from the paper was that rank does not really matter. If you choose a rank value between 8 to 256, it really doesn't matter. Now let's talk about some of the important hyperparameters when it comes to LoRa and QLoRa. So rank, of course, is the first one. The QLoRa paper suggests that 64 might be a good starting point, but again, this is no rule. As such, it's a rule of thumb, and you have to experiment with different values of rank to end up seeing that which one works best for your particular use case. Alpha is another hyperparameter. So alpha basically determines the multiplier applied to the weight changes matrix when you're adding it to the original matrix. So if you want to apply more weightage to the weight changes, or when you're tracking the changes to that particular matrix, you can multiply it with a value called alpha, and that is another hyperparameter. QLoRa paper suggests that 16 might be a good starting point for alpha, but again, you need to try and test different values of alpha to see what works best for you. And then of course there are standard hyperparameters like the dropout ratio, and the dropout here is similar to the one that you use in an artificial neural network. that basically is a percentage that randomly leaves out some weight changes each time to prevent overfitting. And again, you could experiment with different values of dropout, but the paper suggests that 0.1 might be a good starting point. So the question might come out as you do have techniques like transfer learning that are there when you want to deal with the larger models. So why insert LoRA matrices in the first place when you do have things like transfer learning? So the simple answer to that is, when you do have transfer learning, you are only looking at the final layers of the model and you are completely ignoring the initial layers or the earlier layers in the model. And to gain access to those earlier or those intermediate layers of the model, you need to have a mechanism where you are trying to update all of those weights as well. Because in transfer learning, you're only looking at the final layers and you're completely discarding the information in the intermediate and the earlier layers. And therefore, LoRA might be a suitable option in this case. And like I mentioned, in case you are not aware of the rank of a matrix, so rank is basically the maximum number of linearly independent columns or rows of a matrix. I just mentioned it here for the sake of completion, but I'm sure that you are aware of what is a rank. So in this particular video, we tried to understand what is LoRA, how does it work internally. It's one of the most popular techniques out there that people are using for fine tuning of the large language models. And certainly if you're applying for a Gen AI role, or even if you are working and using LoRA and QLoRA, so you should be aware as to how these things work under the hood. So hopefully this video gave you a good understanding of LoRA. If you have any questions, feel free to leave them down in the comment section. If you like this particular video, please press the like button and subscribe to this channel for more such content, because I plan on uploading more such videos, be it regards to generative AI, classical machine learning, interview prep, and so on. So thank you so much for sticking till the end. Have a good day. Take care and bye-bye.